Okay, so now what we're going to do is we're going to have a look at the source code and we're going to see if there are any blaring mistakes in this program. As it turns out, this program is more of a bug than a program. So basically all this program does is we create an array of characters, we then copy argv1 into that array that we just created, except the thing is, because we just use stir copy, not stir and copy, basically we can copy as much information as we want in there as argv1 can be as big as we want it to be. Then we just print it out and then it returns 0. So the main thing we need to note there is we can write as much as we want to the stack and therefore we can overwrite information. Okay, so now what we're going to do is we're going to fire up GDB. So we'll just hit up example. Okay, so what we want to do here is firstly we want to find out the start of where buffer is in memory. So I'll show you how to do that. So that's step 1. Step 2 is finding the size of buffer, and that's actually pretty much all we're doing in GDB. So the way we find the start of the buffer is we use a command called disas, which is short for disassemble, and then we do main. Yes, this looks intimidating, but all we really worry about is this thing here. So whenever we see something that says call, such as these two ones here, then it's just calling a function that we know. Oh, and that shouldn't have happened. Okay, so this is just calling a function we know. So what it's done is it's optimized out printf, and we've just got stir copy there. So the thing that's relevant at the moment is stir copy. So what we're going to do is if we just do one of these ones below, we're sweet. So I'll just do this one here. So copy, we want to add a breakpoint here. So I'll do break here, and we've added a breakpoint here. Now what we want to do is we want to run the file, but we want to print out something distinctive that we will actually see in the stack so we know where it does start. So what I'm going to do now is I'm going to do run Python, and then so there we go. So now what this is going to do is this is going to print 256 A's, and so we've run the program and it stopped at the breakpoint we've put in. So now we're going to use something called examine. So X is short for examine, computer weirdness. I've typed in 200 just because that's the number of spaces that I want to see, memory areas that I want to see. X is for hexadecimal and B is for byte. You can change it to decimal, for example, and word, but personally I find this the best setting. And then we want to set it to ESP because that is the stack pointer. So the thing that we're looking for is a bunch of 41s, like we saw before, just because that means A. So as you can see, these are all 41s. So we've hit the mark. So what we want to do now is we want to jot down this address here. So what this address is this is the start of the buffer that we have access to. So just write this down. Awesome. So now we've got the starting address of the buffer. We're halfway there. So the other thing we need to do is we need to find the size of the buffer. So to do this, what you got to do is, instead of clearing that, I'm just going to quit out of GDB because I am lazy. Launch it up again. Okay, so for this one we don't want to use breakpoints. So what we want to do is we want to run it. We want to use our Python trick again. Except this time we want to keep increasing the number of A's we print until we get an overflow. And we'll know it's an overflow because we will segfault instead of exiting normally. So it is not 260. It is not 264. Ooh, this is interesting. So this does have something to do with everything, but segmentation fault, the thing that we're looking for is this being 4 ones, which you will see now. So it's crashed with 414141. So likely what's happened here is we overwrote the base pointer. So then it was pointing to something that it wasn't expecting, and it was a segmentation fault, or an invalid piece of memory basically. So because we've got this, we know that A's have overwritten this buffer, and we've struck gold. So what I normally like to do is I like to double check this by just doing this. So now if this is successful, they'll all be 4 2s. Done. So the buffer starts at 268. Not the buffer starts, the memory address starts at 268. Okay, this is wonderful. So now we go to crafting our attack. So basically what we do with a buffer overflow is we want to have a NOP sled, and we want this NOP sled to be as large as possible. So the idea is, if we launch the program to return to anywhere inside the NOP sled, it's then going to slide down it, in a sense, until it hits our shellcode. And when it hits the shellcode, that's when we've won. So that is the whole aim of what we do, right? So what we do is we've got 268 bytes of writable memory. So we want to fill that with as many NOPs as possible. But the only other thing we need to write in this space is shellcode. So I've got some pre-prepared shellcode over here. I will open a new terminal tab. Okay, so in the shellcode, I've just got cat shellcode. It does look a little bit weird, and you're just gonna have to get used to that pretty much. Basically, all this does is it tells the computer to launch a shell. This shellcode in particular is 46 bytes long. So we've got 268 bits of memory, right? Then we have to take away our 46, which results in 222. So that is how many NOPs we can write. So what I'm going to do now is we're going to go back to this, and the code for a NOP is -x, because it's like hexadecimal, 90. So this is something that's important. You're probably going to want to get used to that. So now we calculated that 268 minus the size of our shellcode, which was 46 bytes, is 222. So we add that in there. Now what we want to do is we want to add in our shellcode. So I'm going to just paste that. And I should copy it first. There we go, that has been pasted. Now the last thing we need is the memory address. So of the stack, which I'm sure you remember before, I wrote it down. So there is actually an interesting little catch here which you're going to have to note. Basically, computers these days are generally little endian, which means you pretty much have to enter everything in backwards. I could explain it, but I think that's a discussion for another day. Basically, at the moment, you should just realize that that is what you have to do. So it was FFFF CE D0. So we've got that here. So the one problem with this is going to launch us to exactly the start of our NOP sled. The thing is, memory does randomize and does change a little bit, even with ASLR off. So basically what we want to do is we want to ideally launch to roughly the middle of the NOP sleds, then we've got the biggest room for variance. So if things get smaller or bigger, we should be mostly fine. So because we've got 222, if I change this to, like, let's say 3, this is fairly good. Not this one, actually, we'll keep that. We'll change this one to an F. And now when we run it, let's see what happens. And there we go. We have achieved exactly what we want to do. So it's going to print out a lot of randomness, but the main thing that we wanted here is we have now got bin dash. So there we go. I hope you liked this video. If you've got any questions, feel free to just ask them in the comment section below.